This video is an introduction to temperature measurement. This is the first lecture of several that will deal with instrumentation topics. This first video will be an introduction to both the general idea of instrumentation and to temperature measurement. The instrumentation field is big enough that it could be the basis for a course in itself, but not all of you need that much information to become an instrumentation specialist. So the goal in this class is to teach you principles that you can take and apply to any instrumentations that you end up working with as a professional. The idea is that if you can figure out one type of sensor, you can figure out any other sensor we needed. So we will cover a few representative sensors with the concept that if you understand the principles behind them, that you can figure out other sensors too. The instrumentation topics that we will cover over the next few lectures includes temperature sensors such as thermocouples, resistance temperature detectors, thermistors, and integrated circuits. We will also talk about strain gauges and Wheatstone bridge circuits. So our agenda for the temperature measurement lecture includes information about temperature standards, scales, properties used for measuring temperature, and 4 electrical-based methods for measuring temperature. Temperature is a fundamental measurement quantity like length, mass, and time. It is based on a thermodynamic temperature scale with absolute thermodynamic zero at 0 Kelvin and a triple point of water at 0.01 degrees Celsius. Remember that the triple point of a material is when the material is at gas, liquid, and solid forms at the same temperature. There are other defined temperature points, including water boiling at 100 degrees Celsius at 1 atmospheric pressure. The International Temperature Scale of 1990 defines over 15 different calibration points from -272 to 1085 degrees Celsius. Many of the temperatures based on the triple points of different chemical elements. The National Institute of Standards and Technology promotes U.S. innovation and industrial competitiveness by advancing measurement science, standards, and technology. One of the things that NIST does is to provide calibration references for many different measurements. When you buy an instrument, you can spend more to have it calibrate with equipment that is NIST traceable. Within NIST, there is a thermometry group that creates, maintains, and disseminates capabilities to measure temperature and humidity traceable to NIST standards. For more information, please go to the website in the course packet. This slide shows 4 temperature scales. There are 2 absolute scales, Kelvin and Rankine. The common English unit scale is Fahrenheit and the metric scale is Celsius. There are many different ways to measure temperature. This slide shows 3 ways to measure temperature based on thermal expansion. The devices are pretty simple, easy to use, and portable. Mercury Mercury used to be used in liquid in glass thermometers, but mercury spills from broken thermometers pose environmental and safety risks, so they were replaced by safer options. Liquids used can include pure ethanol, toluene, or kerosene, depending on manufacturer and working temperature range. Since these materials are transparent, the liquid is made more visible by the addition of a red or blue dye. Bimetal temperature sensors are generally quite rugged, but they tend to be less accurate than many of the other types of temperature sensors. The principle of operation is based on two metals with different thermal coefficients of expansion connected in a way that a pointer on a dial indicates the temperature. Again, they are simple rugged devices but are not very accurate. Pressure-based temperature sensors are based on the ideal gas law, where the temperature change produces a pressure change that is used to indicate temperature. I just want you to be aware that these types of sensors exist. We are going to spend more time talking about thermoelectric thermometry or thermocouples, resistance temperature detectors, commonly called RTDs, thermistors, and integrated circuit thermal transducers. Here is a table listing 4 electrical properties and the corresponding temperature sensors. Thermocouples are very common temperature sensors because they are inexpensive and rugged. The wires and equipment used is fairly well standardized. You have used the thermocouples in the lab. A thermocouple junction generates a small electromotive force or voltage that can be measured and calibrated against temperature. Resistance temperature detectors are fairly common too. They are based on the fact that the resistance of some metals depends on temperature. The resistance change is quite small, so a Wheatstone bridge circuit is used to convert the resistance change into a voltage change that can be more easily measured. It turned out that the platinum was a good metal to use in RTDs for both its resistance characteristics and its stability and corrosion resistance. For most metals used in an RTD, the resistance increases as temperature increases. Thermistors are another device that has a resistance change as a function of temperature. Compared to the RTDs, thermistors have very large nonlinear resistance changes, so they tend to be used over small temperature ranges. While RTDs have an increasing resistance with increasing temperature, thermistors can have either positive or negative resistance changes depending on the thermistor material. Another category of temperature sensors is the integrated circuit thermal transducers. They are based on semiconductor technology, and what is great about them is that they generate linear outputs in proportion to the absolute temperature sensed. At this point, the temperature ranges are limited, but linear response makes them much easier to connect to standard data loggers. You will see some of them in the temperature lab. This brings to the end of Lecture 15, Section 1 video. The next video will cover thermocouples in more detail. Please write down any questions you have and bring